CFM program for giving me the opportunity to talk today. So what I talk today is about the joint work with Ramin Golesnan in Oxford. So it's related to a couple of topics that are already discussed in this program. So one is the active pneumatics, its orientation order out of activity, and the other is swing at low Reynolds number. So Professor Desimone has already given a nice summary of this subject a few days ago, so I will not repeat too much. But the point is that the unicellular organisms swim in highly viscous, non-inertial environment using active filaments called flagella or cilia. So this is a picture of bacterium, Salmonella diffimilium. It has several flagella emanating from the surface of the cell. And each flagellum rotates like a corkscrew and pumps the fluid. And they rotate either clockwise or counterclockwise, and depending on the direction of the rotation, the flagella get bundled or unbundled. And when they get bundled, the cell swims fast in one direction, but when they get unbundled, the cell stays at the same position. So they repeat these two types of motion. And the right panel shows the cilia on a paramecium. So it has about 5,000 cilia on its surface. And you see a wave pattern. So this wave pattern propagates from the tail to the head of the cell. So it's called a metachronal wave. So first, I show a model of the orientational order in bacterial flagella. So these filaments are the bacterial flagella and cilia are very different types of filaments. So we have a model for each type of the filaments. So first bacterial flagella. So we are inspired by experimental study of the so-called bacterial carpet, which was proposed by the group of Howard as a new kind of microfluidic device that uses the flagella to efficiently transport the fluid. And it's basically a dense monolayer of bacteria called Salmonella marcescens. Only the body of the cell is attached to the surface of the elastoma, PDM elastoma, while the flagella or the tails can reorient due to the flow in the fluid. And due to the flow the flagella generate, they get spontaneously aligned. The left panel shows the flow pattern viewed from the top. So you can see many vortices and also rivers. So it has a size of about 20 to 30 microns. And the center panel shows the spatial correlation function of the flagella orientation and also the flow velocity. So it extends over several flagella. And because of the flow created by the flagella, the transport of fluid is much enhanced near the substrate. The right panel shows the diffusion constant of the tracer particles as a function of the height from the substrate. So you can see that the diffusion is much enhanced near the substrate. Without the flagella activity, this diffusion constant should vanish at the surface because of the no-slip boundary condition. But in this case, it's the opposite. So they propose that this bacterial carpets can be used as a new kind of microfluidic device for efficient transport of fluid in microchannels. And this flow pattern suggests that the orientation order of the flagella is induced by long-range hydrodynamic interaction because there is no direct communication between the flagella. So we model this situation by a very simple model. So we replace the flagellum by a rigid body rotor with a bead at the tip of a thin arm of radius b and height h from the substrate. And we replace the pumping force of the flagellum by a constant force F, which makes an angle beta from the radial direction. And it's also assumed to be horizontal. So ideally beta is 0, but in reality, the axis of the flagellum is deviated from the center of attachment or the pivot point. So we include this angle beta for the case of for generality. And we consider two-dimensional lattice of such rotors with a grid size d. D is asymmetry much larger than the height and the radius of the rotor. Then the flow velocity is given in this form. Here, Fj is the force exerted by the jth rotor, and G is the green function of the Stokes equation. It's not the usual Ose tensor because of the no-slip boundary condition at the surface. When the distance is much larger than the height of the rotor, it's given in this asymptotic form. It's basically 1 over the distance cubed, but it has a anisotropic tensorial structure. So we describe the motion of each rotor by a phase phi I as a function of t. Then the equation motion is just a torque balance or force balance in the tangential direction. So this is a tangential component of the drag force, Stokes drag force. Zeta is the Stokes coefficient. And this is the tangential component of the pumping force. And we solve it for the phase velocity to, Ti here is the unit tangential vector of the trajectory. And we solve this for the phase velocity, which is given as a sum of the intrinsic term due to the self-driving and also the interaction term. So what is in the bracket is basically the force exerted by the jth rotor. It's transmitted by the hydrodynamic kernel and affects the motion of the ith rotor. And omega naught is a characteristic frequency, and gamma is a dimensionless coupling constant, which is given by some aspect ratio of the rotor's system. And r hat is the normalized distance between the I and j.
Could you say a few words, go back one transparency about your little pumping, the right-hand side of the upper diagram, so that the pumping force is the reaction to the fluid being sent out behind.
So, sorry, the pumping force is exerted by the rotor to the fluid.
Yeah.
So what we have here is the reaction force.
It's the reaction
force from the pumping.
So if you go back to that diagram, the
yes, sorry.
The previous one. So when there's a fluid flow past this thing, there's a, if you like, a torque and a force on it, which is in the opposite sense to this reaction.
Yes. It's direct force and the drag force is in the opposite direction.
Yeah.
So this is what this equation means.
Right.
Can I add a question? I mean, the pumping force F has a constant magnitude and the angle beta is constant. It's just the angles phi which vary.
Yeah. Phi is only.
Beta
is
and F can't vary. They're given.
Beta is fixed as a function of time.
And F is
also constant.
magnitude of F.
F is also constant.
Yeah. So there's no elasticity in the system.
No. It's completely rigid rotor. Only the phase is a dynamic variable. And this is the equation for the phase. And it's the sum of the intrinsic and the long-range hydrodynamic interaction term. And this is the parameters. So first we consider the ideal case of radial pumping, or beta equals 0. In this case, the flow created by one rotor tends to align the neighbors in the same direction. And the dynamics is written in terms of free energy, which is in this form. And when the spatial gradient is small, we can approximate the tensor by a unit tensor to get this Hamiltonian, which is long-range ferromagnetic type interaction. So we can compare this with the two-dimensional XY model, which has a nearest neighbor interaction. The difference is that we have a long-range 1 over r cubed interaction. So we solve this original equation on a two-dimensional lattice, square lattice, with a 256 squared, with the initial condition, a random phase as the initial condition. So we show the what we show is the cos of the phase minus the mean of the phase. So when we start from the random condition, we get pairs of topological defects that annihilate by collision. So finally, the system becomes completely uniform, orientation ordered. So we have two kinds of defects, a +1 and -1, the winding numbers. And the plot here is the average distance between the defects as a function of the time. So we can see a power law behavior with an exponent 0.75. So it's faster than diffusion. And also we can develop a scaling argument which suggests that the correlation length should grow linearly with time. So the difference between the scaling argument and the numerical observation is presumably due to a logarithmic correction in 2D XY-like systems. So we can say that it's not diffusion, it's accelerated by the long-range hydrodynamic interaction. And this is a flow pattern. So you can see a vortex rather than a radial defect. So the radial defect and the vortices have the same winding number, +1, but this vortex structure is preferred because of the incompressibility condition of the fluid. So this is corresponds to the whirlpools observed in experiments. Now we tilt the pumps by a constant angle beta. So every rotor has the same tilt angle beta rather than 0. Then we can assume that the coupling constant is smaller than sine beta. This means that the torque created by the interaction is much smaller than the self-driving torque due to the tangential component of the pumping. Then we can subtract the intrinsic frequency from the phase to define a deviatoric phase. For this capital phi I, we can, derive an equation, a simplified equation. So this has a simple form. Beta is a phase delay, and we have a long-range kernel. And we solve the equation starting from a pair of defects here and here. Here we have +1 defect, radial defect, and here -1 defect. So what we have, a spiral waves, a pair of spiral waves develop, and they collide and annihilate and proliferate. And so this is the final dynamical steady state of the system. So it's a turbulent spiral waves.
It could be that your microphone is not working. Suddenly, I mean, for the recording, it's important.
Thank you.
Yeah.
Sorry. So this is the final state. So as we change the beta, the spirals get smaller. And why do we have spirals? That's very simple. So suppose that we have a radial defect here. Then the forces are skewed from the radial direction, and they make vortices around the core. So that's why we have spirals. Because the force is tilted, we have a vortex around the defect. And why it's turbulent? It's more complicated. It's because the interaction is long range. It can be. So why turbulence? It's due to frustration from the interaction. So why frustration? We have one rotor here, then it tends to make the neighbor oriented with an angle beta, and the other pair also tends to make an angle beta. But the first and the third pair cannot make an angle beta, so that's the frustration. So this kind of frustration is expected for even for a short-range coupling, like exponential coupling. So there is a numerical study for exponential coupling with phase shift beta, and in this case, they found a spiral, but only at the core, the phase is random. So this is the coexistence of ordered and disordered states. So they call it chimera states or chimera spirals. In contrast to these chimera states, we have a long-range coupling, and the pattern is globally frustrated or disordered, turbulent. And what we show here is a comparison between the orientational order parameter, orientation and the flow. So this shows the x component of the flow velocity. So we see that the flow pattern and the orientation pattern are well correlated. So next we include thermal noise. Next we include thermal noise. We add the Gaussian thermal torque to the rotors. Then we can define effective temperature. So this is written in terms of rotational diffusion constant and also the coupling constant gamma and omega naught. So this is the orientational order parameter as a function of the effective temperature. So the red line shows the beta radial pumping case, beta equals 0. So we find second order type phase transition from the order to the isotropic states. And this shows the reduced this is the phase diagram. So it's a function of the beta and also the temperature tau. So we get ordered state, uniform state, when beta is smaller than 40 degrees. But if beta is larger than 40 degrees, we get the turbulent spiral waves. And if tau is large, we get disordered state. And we can estimate the effective temperature for a real bacterial carpet by using these numbers. Then we get the effective temperature to be about 0.1. So we are safely in the ordered regime. Now we assume that the pumps are randomly tilted from a rotor to another. So this is more close to the real experimental situation. So because the flagella are bent randomly, or the point of attachment is deflected from the axis of the flagella. So we assume that the beta I is distributed, Gaussian distributed around 0 with a standard deviation, beta naught. And this shows the orientational order parameter as a function of the randomness, beta naught. So we find a gradual decay of the order parameter, and the different colors correspond to different system size. And the blue line shows the mean field theory. I will come back to this theory later. But the mean field theory expects a second order type sharp phase transition. But what we have is a smooth decay of the order parameter. And the right panel shows the standard deviation of the phase velocity. So it's 0 when there's no randomness. The system is completely synchronized. And it starts to grow as a function of beta naught, but also gradually. So we can say that this gradual order disorder transition is not explained by the mean field theory. I think it's due to the projector, the lamp flashes. I saw the lamp is flashing. So the lamp it's not due to the I'm sorry.
Don't touch this part. This part.
Oh.
This
Okay. Okay.
so you
Ah, okay. 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 Thank you. Thank you. Okay. Only. Thank you. So we should take into account the effect of spatial heterogeneity. Now we generalize the problem a bit to a d-dimensional array of rotors with a generic power law coupling, which is proportional to the distance to the power of minus alpha. So in the simulation, we have d equal 2 and alpha equals 3. And we consider this type of equation. Omega I is a random torque, Gaussian distributed around 0, as before. And when alpha equals 0, there is a well-known mean field theory. When alpha equals 0, we have a mean field theory called the Kuramoto model. So he expected a sharp synchronization transition, order-disorder transition. And we can extend this to alpha smaller than d. And recently, it was shown by Chaudhary and Cross that if alpha is larger than 2/3 of d, there is no collective synchronization at all. And I have also extended the Kuramoto model to take into account the spatial heterogeneity and showed that when alpha is in between, we have a gradual transition as observed in our numerical simulation. So I think it's not due to this. So I have no time to go into the details of this theory. If you are interested, please look at my paper. So our simulation corresponds to just the border between these two cases because alpha equals 3 and d equal 2. But we can tune the exponent alpha by changing the boundary condition. Because in maybe I think this maybe I should not use this. So when in bulk we have the oscillant tensor alpha equals 1, and when we are near the substrate we have alpha equals 3, and we can also devise a rotor with 2 wings that makes a force dipole. And if such force dipoles are substrated, we have interaction with alpha equals 5. So we can scan the phase space using this hydrodynamic interaction by changing the boundary condition. Now I'm coming to the second part. It's about the synchronization of eukaryotic flagella and cilia. So this is a picture of Clavidomonas reinhardti, a eukaryotic green alga, and it has 2 flagella, and the flagella in this case has a similar structure as cilia. There are several pairs of microtubules which are connected by molecular motors. And because of the molecular motor, the cilia actively bent in any direction. And this Chlamydomonas swim like a breast-like motion, and it has 2 modes of motion. One is the effective stroke, the other is the recovery stroke. So it's a cyclic motion between these 2 stroke patterns. And recently, there is a very nice experiment done by the groups of Professor Goldstein in Cambridge. And this is, so what they showed is to define a phase of the left and right flagella, and they plotted it as a function of time. The red one is the phase of the left, and the blue is for the right flagellum. And they are well synchronized in this plot. But in other time regime, they are not synchronized. So they found a stage of synchronization and intermittent phase shifts. So there are some minimal models that try to explain the synchronization in eukaryotic flagella and cilia. The pioneering work was done by Geoffrey Taylor in Azorias in 1951. So he modeled the sperm flagella by two waving sheets with fixed waveform. And only the phase difference between the two flagella is assumed to be a dynamic variable. And what he showed is that if the phase difference between the two flagella is 0 or in phase, then they minimize the viscous dissipation. And he assumed a sinusoidal wave form. Recently, this is extended by Elfling and Lauga, and they showed that asymmetric waveform is required for dynamic synchronization. So there are also minimal models for rotors. The simplest possibility is to add a constant torque to rigid body. As a model of bacterial flagella, Kim and Powers considered two helices that are parallelly situated and driven by constant torque. And Riskin and Lentz assumed as a model of cilia two rigid bead rotors with a constant torque. But they found that they do not synchronize. So something is lacking. So next, they add some flexible elements, springs, to these rotors for helices and also to the model cilia, and they do synchronize. So what it means is that maybe the flexibility of the flagella or cilia is essential for synchronization. But our answer is no, because I already shown in the first part that the rigid rotor with pumps can synchronize. And here is the second model that is more suited to cilia. So the effective power stroke and the recovery strokes inspired me to ask to model the driving force as a periodic function of the phase. So we assume a rigid bead making a fixed trajectory R of phi, and the tangential driving force F is a periodic function of F. Then we can calculate the phase velocity by balancing the driving force and the drag force. Here the theta is as before. The prime is derivative by the phi. Now we place two rotors in parallel and look when they synchronize. The flow velocity is written in this form. G is the reaction force of the drag force, and capital G is the going function as before. And the force balance is between the driving force and the tangential part of the drag force. It is the tangential vector. And we can derive the equation of motion for the phase phi. So it's the sum of the intrinsic terms and the interaction terms. First, we look at the condition when the two rotors are synchronized. So for that purpose, we assume that the phase difference delta is small and make a linear stability analysis. The linear growth rate of delta is given in this form. Here F is the force function and H is the form factor of the trajectory defined by this equation. So the in-phase synchronous state is stable if gamma is negative. So for that, the force must be non-constant because here we have a derivative of F. So the variation of the force is essential. Next, for any trajectory in any geometry, we can design a force profile Fy that stabilizes the synchronized state. Geometry means the boundary condition. In bulk, we have the Osen tensor. In a subset, we have the Blake tensor, as I showed before. So it's a very general conditions. For example, we consider circular trajectories with radius b. And we can show that the rotors synchronize if and only if the log of the force function has a positive Fourier coefficient for sine 2 phi. So here are just two examples of such force profiles. This has a sine 2 phi second harmonic component. This has only the single harmonic component. So next, we look at the nonlinear evolution of the phase difference. But you see that the time derivative of the phase difference is the sum of the intrinsic terms and the interaction terms. And these intrinsic terms oscillate very fast, and we don't want to look at this trivial term. We want to focus on this slow term. So for that purpose, we change the variable from the phi to capital Phi. And capital Phi makes the intrinsic phase velocity constant. So this first term vanishes in this new gauge. In this new gauge, then the phase difference is a slow variable, and the phase sum is the first variable, and we integrate it over one cycle to eliminate this variable. Then we have a very simple equation for the phase difference described in terms of effective potential for the phase difference. This is the reduced dynamic equation. And here is the examples of effective potential. The red curve corresponds to a circular trajectory with the second harmonic force modulation, and the blue curve corresponds to a more complex elliptic trajectory with this force function. So we have a bistability. And if the system sits at one of these minima, non-zero minima, then the capital delta is constant, but the phase difference in the original gauge oscillates as a function of time, like this. So this is a non-trivial phase locking state. Finally, we look at correct dynamics of rotors in a linear array. So we assume a rotor with these parameters. This is the reduced to distance ratio. This is the height to distance ratio, very small. And the force profile is single harmonic with a phase difference delta 1. And if delta 1 equals 0, so this is the spatio-temporal plot of the phase. The horizontal axis is the x direction, and the vertical axis is the time direction. And we have a random initial condition here. And for delta 1 equals 0, we get a wave that propagates in the minus x direction. And in this case, the effective stroke, the force is stronger in the minus x direction. So this wave propagates parallel to the power stroke. So this is a so-called simplex wave pattern. But if I change the phase shift delta 1 to 0.3 pi, we get the opposite direction waves, which is called the anti-flex wave pattern. So just by changing this force parameter, we can control the wave patterns. More details of this work will be presented in a poster in the workshop. So summarizing, so we showed that rigid body rotors can synchronize by long-range hydrodynamic interactions, and no flexibility is needed. And our first model with active pumps, which is suited for bacterial flagella, we showed that radial pumping induces orientation ordering via defect coarsening. But if the pumps are tilted, we have turbulent spiral waves or order-disorder transition, depending on the tilts are uniform or random. In our second model, which is suited for cilia and eukaryotic flagella, we assume that the driving force is not constant, but it's a periodic function of the phase. So this is a model for the effective and recovery stroke. And we found the generic conditions for two-body synchronization in terms of the force profile and the trajectory shape and the boundary condition. And we also showed that metacoronal waves in 1D array can be controlled by the force profile only. So that's the end. Thank you very much for your attention.
Yes. You showed that modulating the driving force can give you synchronization and metacoronal waves, and we also know that flexibility it can give you that. Now, if you're thinking real cilia, the driving force, that is to say the bending moment distribution inside the cilium, is determined in part by the load, and therefore it will depend on the phase, because in the active stroke it's far from the boundary, in the recovery stroke it's nearer, so you can imagine the actual force applied can vary with phase, although in a manner that is coupled to the output rather than being given. But also the cilium is elastic. I mean, the actual displacement of a body is determined by the balance of the hydrodynamic, elastic, and active bending moment distributions. So, my question is, what experiment should be designed to test which aspect of is more important in the real system?
Okay. I have two questions. So two answers. So first, there's an experiment using a colloidal system, a colloidal particle, which is driven by optical tweezers along a circular fixed trajectory. So maybe I can show you one. Oh, sorry. So this is actually from Cambridge, the group of Pietro Cikuta. Pietro Cikuta.
Yes.
Do you know? So, sorry. Maybe I should show. So I should show that one experiment by here. Okay, so they drive the colloidal particle along the circular trajectory, and they tune the driving force by tuning the position of the tweezer as a function of the distance from the colloidal particle for each colloid. And in this way, they can modulate the force as a function of the phase. And this is like ongoing experiment, but they are now trying to verify our theory by using the sinusoidal force profile. So in this case, there is no flexibility.
That's right. So this is one end of the spectrum.
Yeah. And also, we have extended our model to include the effect of flexibility by a linear spring for the arm. Then what we have found that if the displacement, elastic displacement, is much smaller than the radius of the rotor, then the effect of flexibility is much smaller compared to the effect due to the force modulation. So that's why we think the force modulation is more important than the flexibility in real serial systems.
Right. Well, let's talk some more in the break of the conversation.
Thank you for that.
When you looked at the synchronization in the bacterial carpets, did you use the far flow field version?
Yes, far field,
of
yes.
tensor?
Yes, we assume the far field.
Is that allowed? Because you really are quite close to the surface.
Yeah. In the real systems, it's more dense. So we should take into account the near field effect of the Blake tensor, and also direct contact between the flagellum.
I think that's going to be important.
Yes, I think at least the entanglement between the flagella could pin the defects and that should be important. We are now extending the model to take into account such aspects.
Well, in your analysis, you fix the force that is turning your beads.
Yeah.
Now, in reality, especially when I think about the eukaryotic flagella, there's a rather complicated mechanism that is driving the cilia and flagella. And you might very well expect that there's a feedback of the forces that are acting on the structure, also on the mechanism that generates the motion. So, how does this affect your...
So you mean that it's not only the function of the phase, but also function of something else in the filament? Yes, I think in reality we should take into account such many aspects of the structure inside the cilium. But this is just a simple mathematical model that shows that force variation only can induce synchronization.
Have you any estimate of the strength of the effects of variations of the internal mechanism that's producing the motion of the...
Okay, so we have no idea about the internal mechanism, but we have compared the effect of flexibility and modulation, and we think the modulation wins over the flexibility effect.
Any more questions?